So let's see number 30. This one says, figure out if this is going to converge or diverge. N factorial over n to the nth. So that one there, right? Okay. So this is a weird one. This is very strange. Because we're not used to n to the nth. But that grows pretty damn quick. But n factorial also grows really damn quick. So this is kind of hinging on two things. If you want to try to do a test for divergence, what would that involve? If you think this might diverge, what do you have to show?
You need a floor that diverges.
Do it one more time.
Use a floor.
Well, if I want to use a comparison test to show that it diverges, but what's the quick way to show something diverges possibly that shows that it didn't have any chance to converge? Yeah. But can you imagine trying to take this guy's limit? Can you apply L'Hopital's?
That does not sound fun.
No, it does not. Because we don't have a definition for the derivative of the factorial for one thing. And the derivative of n to the nth is a very strange little dude by himself. Right? So has anybody else come up across this problem and tried anything yet? No. So what's a really good first thing to do if the test for divergence is not going to help you out, you're not sure what this thing is doing, what's a really good first thing to do for yourself?
Graph it.
Sure. Even better, figure out A1, A2, A3. Get a feel for what it looks like it might be doing. That's not a proof of anything. Right? You can't just tell me 5 elements of a sequence and then tell me, it's decreasing forever. No. If you want to go that way, finish your list out. Go to A infinity. Right? I don't want to do that. You probably don't want to either. So, come up with a few sequence elements, get a feel for what it looks like it's doing. And then that'll give you an idea of, because if it looks like it's diverging, you want to go one direction. If it looks like it's converging, you want to go another direction. So this is the section that gave us the beautiful limit comparison test, which is sort of like the direct comparison test, just easier, right? So if I think this thing is diverging, it's going to inform me what other sequence to put together. If I think it's converging, it's going to inform me of a different kind of sequence I want to put together. You've got to figure that part out first. Get a feel for what this thing is doing. So until more of us try this problem out, I'm not going to go any further than that. So that's my suggestion, is to do that first, just to get a feel for what you want to do next. You don't have a clue what to do next. I don't know what the hell this thing is doing. And to be honest, I mean, certainly, you could try to plug in the calculator. I think the calculator will be okay on the positive side of things for stuff like x to the x. It just gives up on the negative side. It just is empty. There's like, I don't want to go there. All right, so that didn't go very far with that, but that's because neither did you guys. So anything else from homework? Anything else?
Number 36 from 11.5.
$36. Right? The very last problem? Okay. So real quick, while we're doing this, let's remember some things. What's really nice about an alternating series in terms of convergence or divergence? A couple things that are really nice about it. Fundamentally, what is an alternating series? Why is it called that? Yeah, because sometimes it's positive, sometimes it's negative. It's adding, subtracting. So is it harder or easier for it to converge? Easier, because it's kind of subtracting from itself. It's not always building. It's sometimes taken away from itself, right? So that's nice. It's got an easier chance to converge, which translates to the test for convergence is easier. What do you have to show that an alternating series is convergent?
Increasing and the limit 0.
Yeah, so it's decreasing.
Perfect.
And the limit equals 0. And the decreasing part, really, if you look on page, where was it first? Alternating series back on page 727. They give you another type of way to show this. So they tell us, and this is from earlier, some of you guys picked up on this. When I say decreasing, I keep trying to get you guys to take the derivative. And my ulterior motive for that is it works, but secondly, there's another way that works, but secondly, you get derivative practice, right, which we need to keep the derivatives fresh, right? The other way to do this, which some of you guys asked me independently if you could do it the other way, which is fine, is to just compare one element to the next. And you can take the difference and show. So if you're trying to say it's decreasing, then obviously the next guy minus the one before it would be, yeah. Right? The next one will be smaller than the one before it, so then it should be 0 when you take the difference. So that you could show that directly. And they had a couple examples in earlier sections where they did that. But you have to just show those two things. It's beautiful. The limit 0 and then it's decreasing after some point. Okay, maybe. Okay. So for this problem, let me see. Which one was that again? Sorry, Jeremiah?
36.
This one is a little bit more disgusting than the normal one. Possibly. Use the following oh, cool. Okay. So this one's going beyond that. No, yeah. This one actually goes beyond that. I can see that this is alternating. Let's see. N. And somebody asked me earlier about there's only certain series that it can actually tell what it converges to. We have all these tests for whether or not it converges. And I understand the desire to be able to say the damn thing converges to something. But it's very infrequently we can do that. In fact, there was that homework problem where it was like pi squared over 6. And every now and then they'll talk about, well, Euler discovered this or something, and it took them forever to figure out. It was very difficult. It's not easy to tell for just some arbitrary series. Geometric is easy because it's so rigidly defined, right? So there are some sequences that are really easy to figure out what they converge to. So this one, they kind of step you through. So part A says, show that S2n, and I guess they're talking about be the partial sums of the harmonic and alternating harmonic. Okay, so part A, let's define a couple things. Hn is the partial sums of the harmonic. And Sn is the partial sums of the alternating. Now, if I ask you to find the partial sums, how do you do that? I'm getting way too many people in the homework not doing the right thing. Partial sums means 2 steps, really. What do you have to do first? Find the terms. If I want the partial sum, the first S8, that really means the partial sum of the first 8 sequence elements, right? And if you're trying to see, it's not good enough to tell me that S8 equals 15.8 and then say, well, it looks like it's 16. Right? This might be based on a real homework problem. That's nowhere near good enough. What do you have to do to establish a pattern? You're trying to get a pattern here, right? How do I know it's going to 16? Maybe it just came from 16. It's actually going down. I don't know what the hell this thing's doing. Yeah, you have to get S1, S2, S3 up to S8. You have to get all of them so they can see, okay, ones that look like they're all doing. And this is going way back to when we first did limits. You can't look at one guy, you got to look at several leading up to what it is to see what it looks like it's doing. Okay, so this one is talking about partial sums. So HN is the partial sums of this. SN is the partial sums of the alternating version of this. And I guess I mean the form they give. So part A is a little bit freaky. Part A says show that all the even partial sums. Oh, which way is it going? Yeah. All the even partial sums of this guy is equal to this here. So the first thing you have to realize is what the hell does that mean? Right? If you don't know what that represents, you ain't know what you got to do this problem. So what do I probably want to create for myself?
A series.
Good. So I want to look at this guy, for example. And I want to make a little list of his elements, and then I want to make a little list of his sums. All right, so this will be 1, 1/2, 1/3, 1/4. So then I can do his sums. And actually, let's use the same terminology they use here. They call this guy H for the partial sums. Just to keep it separate from the other guy. So H1, of course, would be 1. H2 would be 1 plus 1/2, exactly. Cool. Now do the same thing for this guy, the alternating version. So make a list of A1, maybe up to A4, maybe you might have to go a little further. Then you're going to call these S to go along with their notation for this problem. And you can verify, what do you think you might have to use to do this truly? I mean, you can verify, I'm going to give it away right now. You can verify some base cases by actually plugging specific values in and showing that it works. But you want to show it works forever. Yeah. You might have to use math induction. There might be another way to do it. First thing comes to my mind is math induction. Trying to prove some general statement like this. And why does it feel like the most basic math induction? I know some of you guys really love math induction, but the most basic idea of math induction is what do you keep doing and you have it equal to something? What's the most basic one? We did several of the first problems were like this. I just kept adding, right, like a series. So it makes sense that these partial sums, if I want to prove this statement, I might use math induction to do it. When I add the next one on this side, does it actually add the correct thing on that side? Does this side become what it's supposed to be? Maybe. But until you've done this work to really see what it looks like these things are doing, you can't even start to tackle that. So it's a lot like the last one we did. Until you make those lists for yourself, you don't know what it looks like things are doing. Okay, maybe. All right, so that's what I give you. That's a little hint on how to start that one. And it's interesting, in part B, they reference exercise 44 back in section 11.3. If we look at what that is, I like it. It doesn't really help out too much. You could always hope it's going to help out a little bit. So what you want to do is do a few of these. See if you can write a general term for HN. Right? And then see if you can write a general term for SN. And what does this really mean? What does that S sub 2n mean? It picks out what? Even ones. S2, S4. So you want to pay attention to S2, S4, S6 and see if there's some kind of pattern within them. But again, if you don't have that list to look at, there's nothing to talk about yet. So try this problem out. Try to make that list If enough of you have done it by next time, we can try to do this problem together. Okay. So anything else from homework? All right. So like I said, last time we got up through 11.5, alternating series. Let's see, I only have one poor little handout dude with me. So if you didn't get the handout, there's one. If more than one of you needs it, you could just email me. If I think about it, I could put it up on the internet if somebody reminds me. Let's try a couple of these real quick before we move on. From like 11.4, 11.5. So here's one. We saw one like this before, and we had to do something specific with it. It's number 10 back in section 11.4. So this is not 11.5 yet, but be very careful. Is this an alternating series?
Yeah.
What's being done to the sign? Squared. So if it does go negative, it actually doesn't because it's squared, right? So, and it wouldn't even be truly alternating. There's we're going to get into section 11.6 today where we talk about what if it doesn't alternate, like the first one's negative and the second one's positive. What if the first 3 are negative and the next 10 are positive and the next one's negative? And the next 6 are positive, and the next 7 are negative. Some weird pattern to it, right? We're going to have a general way of attacking those things. So this is not alternating. It's not even time to do that yet because it's not section 11.5, but still, just to point out, just because it's a trig function and it's being squared, so it's not alternating. What does it look like it's trying to be? So where am I moving now when I say that? When I say what does it look like it's trying to be?
Limit test.
Yeah, I'm going to go for the limit comparison test, right? So we don't have to use direct comparison anymore. Limit comparison is beautiful for this. It's now nowhere near as precise, nowhere near as technical as a direct comparison test. But that's one reason why, personally, I love the direct comparison test. But
So like 1 over k squared.
beautiful. So again, if you take the piece out, that's, of course, this guy goes between 0 and 1 because it's squared. So if you kind of move him out of the way, you end up with something that looks like it's 1 over k squared. And I know that that does what? 1 over k squared. What's that series do? Converges. I love it because it's a p series for p is greater than 1. I love it. Cool. So how does this limit comparison test work? What's got to be true to even be able to use it? Or is there anything that has to be true that has to be able to use it?
It's be decreasing and limit has to be and it has to be a real number. The limit has to be
Yeah, the limit has to be between 0 and infinity, because otherwise it's going to be, and I don't have to know that beforehand though, so it's not a requirement going in. If I get one of those things, it's indeterminate. The test doesn't know what to do. So the only thing you really need is positive terms. That's all you need. Right? And to be completely honest, it should also make sense that if they were nothing but negative terms, I could do something similar with that. Right? So this test just requires that they're positive terms, and the limit is what I look at. The limit of what? What do I look at for this? Limit comparison. So here's my, what do I call this? AN. And of course my BN is going to be that 1 over k squared. So let's call it K. AK, PK. 1 over k squared. So make sure your index matches the controlling variable. And the beautiful thing about this process, you just take the limit of AK over BK. It doesn't matter which one you put on top, really. Okay. Yeah. The ones we're used to. And you see this do what I pointed out last time, but that K squared on the bottom is going to come up and fill in the other dude, right? Become the sine squared. Now as K goes to infinity, what does sine squared do?
It becomes irrelevant
Yeah. Right? Why?
because it's got that k to the third outside of it. That k to the
Yeah, so sine squared is kind of contained between 0 and 1, 1 at most, right? So the limit, this guy's limit,
It's gonna be one.
yeah, this gets a little bit strange with this sine squared in there. So, but is the limit really 1? What is the top sometimes? Possibly.
0.
Could be 0 sometimes, or close to it, right? And of course, the biggest the top could be is 1. But all I know, what the important thing is the limit 0 or infinity. Well, it's not infinity, that much we know for sure. Right? Could the limit be 0?
Yeah.
How? It's definitely not 0 either, because it doesn't settle on 0. Right? So what's weird about this one is it's oscillating forever.
So would you say it's undefined or something?
So this is a really good example. Once you learn limit comparison test, you might think you've left direct comparison test behind. But this limit, can you really do it?
No.
So you got to be careful. You can't just say that the limit is somewhere between 0 and infinity, so you're done. Because you don't know what the limit is. You can't find it, truly. And if I was a little less stringent, you could probably get away with that. So you almost have to use direct comparison.
Then can you just pluck off the sign?
Yeah, then you can just pluck off the sign. Cool, I like it. But you see that limit, that stupid sine squared piece makes the limit an oscillating problem. And then I can't say the limit is anything. Is the limit equal to some L? No, it's not. The limit officially does not exist.
And that's because it oscillates.
Because really, what's the coefficient of k cubed on the top?
1.
No,
Oh.
it's sine squared. Okay. So if you want to do it that way, the limit of this is sine squared k over 1. And what does sine squared k do? Oscillates. So either way you look at this, you're kind of screwed with this. Normally this is awesome. Normally this is beautiful. But those trig functions find a way to mess anything up. So I need a method where I can just get rid of the damn thing. So it's these oscillations. It's because of the fact that this is a limit comparison test. And limits of trig functions can get tricky because they oscillate. So if I go back and I do a direct comparison, I know I want to eventually get here, right? To that kind of thing. And it shouldn't be too hard. We know it does what? We really know this does what?
convergence.
We know it converges. We're just trying to show it. We know it converges already. So do I want to have a ceiling or a floor?
Ceiling.
Definitely a ceiling to keep me down. So I want to make this bigger somehow. Something that's bigger than this to be my ceiling. So obviously the first thing you do, sine squared itself is less than or equal to what?
1.
1. So just by taking that guy out, you've made this work. Let me stop right there. You guys see that part? Sine squared itself is less than or equal to 1. So that is a true statement. Replace sine squared with 1, you've made something that's always at least as big as this thing is, if not bigger.
Because it's basically just going to be K.
Yeah, you're replacing this guy with 1. And by doing that, you make him as big as this guy ever is. So this is definitely a true inequality. Now, what's still in my way? The 1. Now, if I took that away, is the inequality going the right direction?
Yeah.
Yeah, if you make the bottom smaller, you're making the whole thing bigger. This is nowhere near as bad as it could have been, right? Some of you guys should know how bad these could be. It only gets bad when the inequality goes the wrong direction, when you want to get rid of what you don't like. There, I want to get rid of the 1 plus, and it makes the inequality go the right way. I created a bigger thing by doing that. Since this converges, this smaller thing must also converge. Cool. So this is conversion. So that's a really good problem. I didn't realize it was going to even be like that. It's awesome. It shows a possible limitation on the limit comparison test. So it's trig functions that get us.
Just a question. So is this kind of like one of the only circumstances when you would know not to use the limit, or are there other type of situations where you know that you don't want to use those?
Any function that might have some kind of oscillatory part of it. So trig functions are the first things that come to mind when you think about that, right? There are other functions that have oscillations in them, but they have to be infinite oscillations. So obviously no polynomials, because eventually polynomial decides if it's going to go up or down forever, right? So mostly trig functions you got to be careful about with that. But it's anytime you get to a limit where you can't determine what it is. Either it's 0, infinity, or you can't figure it out. Those really are the 3 situations where the limit comparison test says, I don't know. So we thought there was 2 because 0, infinity, but the third one is if you can't even say that equals L. You can't fill that blank in. The limit comparison test can't say anything. Good. All right, let's see. I knew there's a reason why I wanted to do that one. I just forgot what it was. Oh, so what about this one here? Number 20. Let's see why I picked that one. I picked these a while back and now I can't remember why. So what does this look like it's trying to be, except for a part of it? Totally geometric. I like it. We have numbers to nth powers, and it looks like it's trying to be convergent or divergent. Convergent, because that would be 4/6 less than 1, right? Just the top and the bottom have some n that they keep adding to it. But this sucker here is going to get stupid big compared to that very quickly, right? So, which method would you use here? I think I remember why I picked this one. Let's try limit comparison. Try limit comparison. So what would you compare this to? Based off of why we feel this converges, what would you compare it to?
Just 4/6.
Yeah, 4/6 to the n, right? But otherwise known as 2/3 to the n. I like it. So if you try that, so if you call this an, bn is 2/3 to the n. Let's see how weird that gets. So the extra n piece you got to be careful about. gets kind of neat, so you're careful about it. Let me give you a little hint. You might want to consider these as two separate things. And then it does really nifty stuff. And you could consider it this way too. That'll do the same thing.
And then just goes to 12 at the end.
Yeah, I like it. So maybe start getting used to just multiplying by the reciprocal of this. That'll make this a little bit quicker to write. Reciprocal. There you go. So pretty cool with that?
Yeah.
Divided by that is multiply by reciprocal. So if you multiply that through, what do you get? 3 to the n times n?
Plus 12 to the n.
Because of this same exponent, you can put those together. I like it. Over 2 to the n, n plus 12 to the n. Yeah, what's going on here?
It's just going to go to 1.
Will it? Which one's growing faster, the top or the bottom? Yeah, why is the top growing faster? Because the 3. You guys see that? Because of that guy. So this is definitely going to go to, which means the limit comparison test is inconclusive, right? It doesn't mean anything. It doesn't mean the answer is the opposite of what you thought. It just means the limit comparison test doesn't know. So I think I picked this specifically. I picked these two because it shows you when the limit comparison test doesn't really work that well. This is a lot easier to do with the direct comparison test, and so is that one. That was much easier to do with direct comparison, to be honest. Now, because I also don't want, because when I first introduced this, it's definitely very much easier than direct comparison when it works. And it works a lot. But I wanted to give a couple examples of it doesn't always work. So this is where you got to be careful about, okay, I made a mistake. This doesn't lead me somewhere. Let me go back and try something else. So I'll go back and try direct comparison. And I feel like this, we think it converges. Let's see if we're right. So I want to create again a what? Ceiling. So I want to find a function that is bigger than this guy, at least. So which one of these can I just take away and it's true? The bottom one I can just take away and it's fine, right? Now the one on the top is going to be the one that's a problem. But not that big of a problem. Let's see if you guys get this. If any of you are the people I've talked to about this kind of problem, when you can't, why can't I just take that away? Yeah, because then the inequality would be pointing the wrong direction. You need every single one of these pointing in the same direction for this to be a proof. So when you can't just take it away, you want to make it like terms. So definitely replacing n with 4 to the n makes the top bigger. Let me stop there. You guys, that's the point I was trying to make. I don't know if I've said that a lot in general, but I've said that a lot to individuals who've asked me. When you can't, now the bottom I can just take the n plus away, right? Because it makes the inequality go the way I want it to. I can't just take that away. Which means I need to replace it with something that is always bigger than this. And I can replace that with n squared. That's always bigger than this, above 1. So it always has to be bigger after some point. But that wouldn't make any sense replacing it with n squared. I'd be in the same damn place I am now. That's why I want to replace it with something that's like terms with the other thing that's there. Because it maintains the main reason I thought this converged. That 4 over 6 to the n. So what is the top now? Don't say that. I'm going to cry. It can't be 8 to the n. I have n 4s, but how many 2's do I have? 1. What's x plus x? 2 times x. So what's 4 to the n plus 4 to the n? 2 times 4 to the n. Now why is that not 8 to the n? Because I don't have enough 2's. I have 1 2. How many 4's do I have to put it with to make n 8's? I have to put it with n 4's. I don't have enough 2's. You guys see that? And then order operations. Do you multiply first or do you raise? To a power. Do you do powers first or multiply first? Powers. Order operations are there to save you from yourself. Do you guys understand? If I had 2 to the n times 4 to the n, what's that? No question. We already did something like that earlier when we had 12 to the n up there, right? The only reason I was allowed to do it is because for every single 4, there was also a 2 to go with it. So I ended up with n 8's. Here, oh, I got one poor little 2. He's not enough to spread himself out for freaking... That sounds horrible. What a horrible life that 2 has. We won't make him do that, right? Sorry. I've got a Sting song singing. Now, what is this definitely? How can we write this? 2 times... So does the 2 matter? Yeah, I kind of gave it away the way I asked that question, but it doesn't matter. It's just the first element, or it's part of the first element. What matters is the r is less than 1. So this series converges, and since it's bigger than mine also has to converge. It's my ceiling, right? So this converges. All right, now that reminds. Okay, I picked those last week, and then this morning I was like, why did I pick those? That's one. Okay. But don't, hopefully this doesn't have the opposite effect, and you just suddenly don't trust the limit comparison testing. That's what I would try first most of the time. It's going to be beautiful most of the time. Sometimes the limit just doesn't come out. Then you have to take a step back and use something else. Alternating series, please let that be nice. Please let that be nice. Let me ask you this here. What does that do? Let's figure this out here. How is that different from 1 over n? This guy is sometimes negative, sometimes positive, right? So it should be a lot easier to converge. And 1 over n is sort of like this thing that's right on the edge anyway. So it just needed a little push. And this is huge. We just took an infinite number of its terms and made them negative. So now it's not always adding to itself. So it should totally converge. So how do I use this alternating series test? What do I have to show? So what? First off, what's my an? 1 over n, beautiful. That alternating part is kind of like considered to be separate. You want to investigate an. So I got to first show that an is decreasing. Right? And to me, the easiest way to still do that is just take the derivative. Yeah, so that's minus 1 over n squared, which for n from 1 up is definitely less than 0. Not for all n factorial, sorry. For all n. So it's decreasing forever. And then I just have to take the limit. So as long, if I have a series, I don't care what the series is, this is awesome. This is what you guys have been hoping was true since we first started talking about series. Just take the limit and show it equals 0. You can't do that unless it is alternating. It doesn't mean anything by itself unless you have an alternating series. So is the limit 0?
Yeah.
Of course. Limit n goes to infinity. 1 over n is 0. Therefore, this guy converges. I love it. So as long as the limit is 0, and I showed you that picture last time where we said, okay, the first term is here, and then the second term you're going to subtract a little bit, and then you're going to add a little bit less, and then you're going to subtract a little bit less. So as long as that's true, you keep moving by less and less, which translates to this. As long as you do this, you're moving by less and less, you will home in on something. If you start moving less and less and then start moving more and more, you're just going to bounce to infinity and negative infinity, like 2, -6, 18, like that one did. Maybe that's why these requirements make sense. Okay. Maybe. Let's see. So what about this one here? Let me give you one with the trig thing in it. This might be homework, I don't know. So I can tie my shoe before I kill myself.
The homework form.
Kick ass. Do you not want me to look at it?
That's fine.
I thought that might be all right. So if anybody turns this problem in wrong for the homework, I will wonder about you. The funny thing about this, what should you always do first when I'm asking you if a series converges, diverges? What should you always do first thing? Take the limit, because that's also called the test for divergence, right? If the limit of this is not 0, then it doesn't have a chance. Now, don't go overboard and say if the limit is 0, I'm done. No, that just means you got more work to do, right? And what's beautiful about doing that for this thing is that's one of the things I got to do for the alternating series test too. So what is the limit? And what's my AN first off? And is this truly alternating? What does that do?
-1 to 1.
So another way to write that. What is it first? When n is 1, what is it? What is the value of this? -1. So they didn't even have to write it like this, did they? All this thing does is it represents -1, 1, -1, 1. So you could actually replace that with -1 to the n, because I want the first one to be negative. Yeah. You understand? So cosine n pi ends up doing the same thing that -1 to the n does. It's because it's a multiplier pi in there, right? That sine k earlier, k was radians. It could be anywhere, just not any specific pattern to it. You see the difference there? It's because here it's multiples of pi. All right, so all that stuff aside. What is the limit as n goes infinity of this? Let's make it official.
0.
That's screw it. We can do it like that.
0.
Yeah, totally. And one application of L'Hopital's would tell you, or if you don't like it, the bottom is just growing so much faster than the top. But if I do L'Hopital's, what would I get? In which case, part of me just won't let that happen. We got to make it real numbers to do this.
1 over
Yeah, 1.
dx natural log of 2.
Beautiful. Which is solely going to 0. Right? Cool. Yeah, we looked at that derivative before. That's going to come up over and over again. They love putting these. They love putting this kind of thing in series. 3 to the n, 4 to the n. So you will have to do derivatives every now and again, so just don't forget, it's a very simple derivative. So it's not divergent. It has a chance to converge, and part of the alternating series test has been shown. What was the other part? Decreasing. Which means take the derivative. Take the derivative of what? You're really careful about this. That's why this one is a really evil problem. You identify AN by putting the alternating part aside. So that is not a part of what you have to take the derivative of. That would be a little more heinous. You with me?
Yeah.
So when you're doing these two steps for the alternating series test, you're talking about AN, the what's being multiplied by -1, 1, -1, 1. You take that aside for a second. Or take the absolute value of it if you want to look at it that way. So it's a lot better for this derivative. So make it into a real number. And I like this kind of problem because you got to do L'Hopital's there, and this is a true derivative, so you can't just take the derivative top and bottom separately. That's L'Hopital's. Good. So it's x prime, which is 1 times that, minus. Good. So minus, leave the top alone, derivative the bottom. All over 2 to the 2x.
Or 2x.
Cool.
How do you know if that's
Yeah, how do we know if that's decreasing or not? The bottom is always positive, so I'm not even going to worry about the bottom. It's positive. It's not going to mess with the sign. All I care about is the sign now. So when is this? And before I even go there, what can I do with all those 2 to the x's there? I can cancel one of them out. So I get 1 minus x ln 2, which to some of you should look very familiar. It should look a lot like the problem I asked on the last test. And I want to know when that is negative, so less than 0. So I get x has got to be bigger than 1 over ln 2. And what is 1 divided by the natural log of 2? Somebody help me out. Help me.
1.44?
Cool, 1.44. So as long as all it needs to do is be decreasing eventually. And it's not decreasing from n equal 1 to n equals 2, but it is decreasing starting at n equals 2. Because that's bigger than 1.44. That is very much like that homework problem I gave you. Not homework, the test problem, number 6 I think it was the last test. Oh yeah, on the bottom, but it's always positive. So the only way to make this fraction negative is to make the top negative. Cool, I like it. Okay, maybe. Okay. So just remember, alternating series test, 2 main things you have to show for it. All right, so let's get into this. This is something that the book introduced a while back, but we haven't made a big point of this yet. Now that we're getting into this talk about alternating series, and then we have the series that goes back and forth at weird intervals. The first 7 are positive, and the next 20 are negative, and the next 2 are positive. Oh my God, we can't do this kind of thing. It's not truly alternating then, so the test wouldn't work. So what we do then is we look at, so if I'm given some series like this, it doesn't even matter what it is. If Now think about that. Why does that just make sense? We actually, this was introduced a lot earlier, this idea here. This is a small part of this next section because it just kind of brings it back. But why would that just totally make sense? If the sum of the absolute values of all the terms converges, why would this definitely have to converge? Maybe they're all positive already, so these are the same series. That's the worst it could be. If they're not always positive, then some of them are negative, right? Which means this guy has to converge. If this guy converges and he makes everything positive, and he still manages to converge, then this guy, where some of them could be negative, he's totally got to converge, right? He's going to converge to a smaller number. He's going to be even more convergent. He's going to converge to a smaller number. Does that make sense? Again, I don't want to play poker with 90% of you people. So, if this is true, we call that being absolutely convergent. So if this is true, the sum of an absolute value converges. We call an absolutely, like totally convergent. Which makes sense. Kind of is nice. That word absolutely serves two purposes there. It is absolutely convergent. And there's absolute values there. So it's like a horrible pun, but we'll get past it. So, for example, very, very easy one. Why is this absolutely convergent here? Because the absolute value of it would just leave 1 over n squared, which is convergent, right? So that means that this is absolutely convergent. There we go. So this is absolutely convergent because the absolute value of an is 1 over n squared, and that's a p-series p greater than 1. So it converges either if you leave it in. It definitely converges if you leave it in. And then I can just use an alternating series test. But I don't even have to do that. I want you to realize you could take the absolute value, show it's convergent, and be done with it. If I gave you this problem, you don't have to do the 2 steps for absolute convergence. You just have to do this. It converges when you take the negatives out. So hell yeah, that converges. Done. Next. Yes, ma'am.
What happens to the n in -1 to the n?
How do you mean, what happens to it?
Because after, when you take the absolute value, it's 1 over n.
True, because if I take the absolute value, I get 1 to the n, which is always just 1. Yeah. So it's there. What about this guy here? We'll take a step down. I like it. So this series does what? We looked at this one earlier, didn't we? Isn't this one of the ones we did earlier? This is certainly convergent alternating series, isn't it?
Yeah.
We did this one earlier. So here's what you call it if it's not absolutely convergent. We call this one conditionally convergent. On the condition that you don't put absolute values on me, I am convergent. So that's why we call it that. So this would be called conditionally convergent. We showed earlier that this converges because it matches everything that the alternating series test requires. It's decreasing. We took the derivative. It's going to 0, definitely. 1 over n goes to 0. So convergent. But it's conditionally convergent because if I look at the absolute value, that does not converge. So we officially call that conditionally convergent. Cool. And from the beginning, we knew 1 over n diverges. So just putting that in is the condition it requires to be convergent. So that's the other way to look at it. How's that doing right there? So that's just some terminology, but this is kind of important terminology. I'm going to ask you, show if it's this, or if it's just that, or if it's neither. The only way to be neither is if you diverge. Cool. Oh, let me go ahead and give you this here before I forget. So we just talked about the first little piece of this handout. So when you get the handout, try out the first set of problems at the top. So guys, on these first few, just tell me, do they diverge? Are they conditionally convergent, or are they absolutely convergent?
How do we know if it's neither?
If it's what? Oh, then it diverges. So your test for divergence would show it. Divergence. Because what do you have to do to show an alternating series convergence? Yep, as n goes to infinity, and that's the same thing you do to test for divergence. So depending on how that comes out, you either keep going or you stop and say it diverges. Yeah.
So if it doesn't equal zero,
If it doesn't equal 0, then it's divergent. Yeah. Then it's not convergent in any way. Yeah.